Do you know by heart how much images we have or products or?
Yeah, we have roughly 40 million products.
Jesus.
These are products online.
In data science, you have an input, and then you feed the historical output, and then you get some kind of an algorithm. So you get a model that has a predictive power that when you give it an input, then it can give you the outputs.
Fun fact: the first 1 million images were indeed embedded locally in a weekend on the laptop.
On the laptop.
Just turn it on, and I was like, "Let's see Monday."
Oh no. All right. Well, it's been quite some time. I think around 1.5 years ago or so. We both were at the conference from Bol.
Yeah.
And we saw a really cool topic presented by the two of you.
Yeah.
Really inspiring. And I think at that time already, I think after your talk, we approached you and we were like, okay, we should do this on the podcast. But life happened, and well, it was really hard to just find a gap that all four of us could attend. So really happy to have you both in the studio today.
Happy to be here.
Yeah.
Thanks a lot.
Yeah, and we're gonna have a kind of romantic topic today, Cupid. But sounds mysterious, but we will explain later, of course. Maybe we can start with introducing yourselves.
Would be nice.
Sure.
Yeah. So I'm Thijs Roukens, data scientist in Team Smart Assortment now. So 1.5 years ago, it was actually still called Team Tulip. That still doesn't help you where I'm at. So basically, back then we were in the pricing domain, but now since January we are also in the content, assortment quality, offer highway, and promotions. So that's quite a big scope.
Yeah.
But we only focus on the data science topics around those topics. So there are a lot of engineering teams around us, and we help them out if there is a data science challenge, and that's where we shine.
Yeah.
So I've been at Bol now for almost 6 years. Started as an intern in forecasting. Actually, I started during COVID, so the first week of lockdown was my start period.
Okay.
I was onboarded online for the first as the first batch, which was fun.
Lucky you.
Yes. It was really cool actually to be in Bol at that period. So it was like a lot of challenges, especially in the forecasting team, because the whole sales data was changing. There was a big big change in time series. Yes.
Yeah.
So after that, I stayed for 2 years in forecasting, and then I changed to the pricing domain, where I actually that was the first time I interacted with Gokhan. Living in Rotterdam, I like to play a lot of sports. I play squash from quite a high level.
Okay.
And that's it.
Awesome. And your background, maybe I missed it. But data science or engineering?
My background is in econometrics, so the data science.
Perfect.
I see.
Yeah. I really learned engineering on the job.
Yeah, that's awesome.
Nice. I'm Gokhan. I'm also a data scientist and half engineer-ish in Team Smart Assortment. Been at the company for almost 5 years now. So I also started out as a YP, just like Tim, as a young professional. I was an engineer for a full year, and then I switched over to be a data scientist. But I still hold on to that engineering route a bit. Besides that, I live in Amsterdam. My background is in computer science and data science. So also by education, I have a bit of an interest in both.
Yeah.
I live in Amsterdam, and in my spare time, I watch a lot of movies.
Oh, okay.
So
what genre?
my letterboxed link.
I know. I like it.
Cool.
What genre? We have a movie geek here as well.
Oh, yeah. I love movies. Man.
Okay.
What kind of movies do you like?
I don't necessarily have like a specific genre.
Yeah.
Right now, I am watching a lot of like older classics that I have kind of missed. There are a lot of these movies that like I have never watched. Like the next one is The Green Mile, for example.
Oh,
I've
okay.
never
Oh,
watched
yeah.
The Green Mile.
Yeah, that's like a classic indeed. Yeah.
So I'm like filling in the blanks.
Yeah. Nice. Working on your education.
Exactly. Yeah. What about you?
Yeah. Good for you. Yeah.
Do you have a kind of movie genre that you like?
Well, actually, yesterday I went to also another classic, Back to the Future, in the theater.
Like
It was a 40 year anniversary. Yeah. It's but it still holds up.
Nice.
It was it's awesome.
Yeah.
Was it restored? Was it like a 4K restoration?
I think so. Yeah. I think
I
so.
need to see that as well.
Yeah. Classics.
Yeah, it's awesome. So let's dive into the magical world of data science today. And like honestly, for me, I still have to get used to the new names. But like every time I hear someone talk about things Team Tulip was doing, I always got like a really cool feeling because I felt like the team that you both are in, are doing really cool things here at Bol. So could you maybe shed a light a bit on, indeed, you already mentioned the department you're in, but what you're doing, what data science is here at Bol, and well, what keeps you up from day to day?
Give this one to you.
Okay. So our team is a bit of a different structure compared to other data science teams or other teams in general. So we are not part of a specific product group, but we work with multiple products. So we have a larger scope. And as a data science team, we are somewhere in between like product analytics, where we sort of provide guidance and a bit of a how do you call that? Consultancy to software teams. But on the flip side, we also have our own OPEX. So we have our own applications that we use to interact with these teams. And how data science sort of fits into here is whenever teams have problems that they cannot solve with traditional algorithms or traditional sort of rule-based working, that's where we utilize a lot of the data that we have in Bol, such as like product data, such as pricing data, customer behavior data, and we use this data to predict for cases that we cannot figure out with traditional algorithms. There is this like famous image that I like to use a lot for data science, where in traditional programming you have an input and an algorithm, and then you get an output.
Yeah.
Whereas in data science, you have an input, and then you feed the historical output, and then you get some kind of an algorithm. So you get a model that has a predictive power that when you give it an input, then it can give you the output. So the paradigm is shifted a bit. So we use this paradigm to help out in pricing. That's where Team Tulip is from. And we also touch upon a lot of catalogs, so product information. We help with assortment quality, sort of which products should or should not be on our platform, and also offers.
Yeah, that's nice. And also a really big chunk of data, of course, where you can do a lot of really nice experiments with.
Yeah.
Because you have to remind me again, what was the topic of the presentation we went to again?
Yeah, so that project actually started in pricing because, well, we have a lot of products at Bol that are also sold across different platforms, such as MediaMarkt, Coolblue, Amazon. And of course, for us as a platform, it's really interesting to know what is the competition doing, because it would help you to set better prices. Because customers, of course, are browsing the internet to get to the best price to the best price. Delivery time is also kind of important, but price is quite often the most important factor.
The Netherlands.
Exactly. So yeah, it's of course very good or important to know what the competition is doing. And usually, like before, data science was a thing in this domain. This was done using AON numbers, so European article numbers, and then it was just exact matching. So if Amazon or Coolblue or whatever competitor has this product as well, we could do matching based on this number.
Yeah.
But this, of course, covers only some part of it, because mistakes are made, right? AONs are filled in wrongly, or maybe different AONs are being used. There are multiple reasons why this was failing, but it gave us not enough coverage to really know what the market is doing. So we actually thought, okay, what can help? I think it was even a YP project from you to start
really?
off.
Oh wow!
Yeah. Yeah, so we started
That's cool.
Yeah, it's really cool how to see how it also went from start to finish, how much impact it's making now. But we started with okay, then we are going to compare titles, for example. That's one is actually, besides Aeon, if the Aeon is wrong, but it is almost the exact title or very close in title, it could still be a very valid data point. We found out it's a bit noisy, titles. People are title stuffing quite a lot. But the one thing that is quite consistent is actually images. So that's then where we actually started the project to use image comparison. So instead of Aeon comparison, we use image comparison. And this is, of course, way more difficult than Aeon, because then you can just, well, Aeon is just checking if they are equal. Image, yeah, you can check if pixels are equal, but they barely are. If you have a different image size or whatever, it's already a challenge. So that's where we needed data science to set it up. And that's, where we are now also going to talk about, I think.
Yeah.
It's really cool though. So you're given like some sort of challenge or some big issue that we're seeing on a scale of an e-commerce company, as Bol of course has. Do you know by heart how much images we have or products or?
Yeah, we have roughly 40 million products. These are products online.
Products, okay.
And online.
This is also only online.
Cool.
So you also have like a lot of stuff that is offline. If you roughly say 6 images on average per product, you're talking about 240 million images to process.
That's cool.
I think even more than 300 million, I think.
So how do you start as a team? Like this sounds like a huge thing to tackle, of course.
I actually think here the engineering background of Gokhan was really, really helpful. So you can better explain how we did this.
Yeah. This is, when you look at it from a scale, it's a huge issue to tackle all at once.
Yeah.
So how we did it, indeed, you first start with like a simple idea, and that idea was indeed text. And then you apply this small idea to a small chunk. So we started with like only a very limited amount of products that we saw, okay, for these, we don't have a lot of competitor products. We don't have a lot of matches with competitors. So then, okay, can we build a system for this small chunk and where we can do some reliable matching? And this is also how we came to, okay, probably for these products, the titles are not working that well. Let's look at other unstructured information, because the images probably are a lot more difficult to modify for a seller. They just get the image from a catalog and then use it to sell on our platform. So this is all learnings based on this small chunk of products. And the first time that we did this, of course, you get some results, but you don't know if these results make sense. So there was a lot of manual checks from our end, and also we took the help of our operations colleagues. So there was a continuous process of, okay, we have this new predictions. Can you take a look and say you think that they are the same products when you compare it to the competitor? And here then we started to build up, okay, at first we said, let's take a look at some chunks. Let's take a look at some chunks that we cannot really match and try to do this on a chunk level. Then we realized, okay, we have way too many chunks on the platform. Then what kind of granularity can we go for? And now we basically do look at almost all the products on our platform, except for some products that, like books, that we do not necessarily need to match because books have ISBN numbers. They are very reliably matched all the time. So or some products that are very, very long tail, so they don't even get visited. We exclude those, but besides those, we currently have, I think, 20-something shops and again, 200 million images that we process, and we look at all the new ones coming in daily. So basically, we built this up from a small scale application to just larger and larger scale. And in this process, also, what started out from doing stuff on our local machines, then went to first Kubernetes, then it went to, okay, we need even bigger machines. So then we went to Vertex AI, which is Google's sort of hosted AI platform. And now we have these huge jobs that are being done every single day.
Yeah, impressive.
Fun fact: the first 1 million images were indeed embedded locally in a weekend on the laptop. Just,
on the
just
laptop.
turn it on and I was like, let's see Monday.
Oh no, poor laptop.
It did well.
No weekend for yeah.
Yeah.
Reminds me of Bitcoin mining in the beginning.
Basically.
Before
On
you
your work
could
laptop.
needed the farms, but you talked about embedding. Huh? What's embedding in this context?
Yeah, so I actually think this is indeed the core technology, the most important technology of this project, because you can envision, like, of course, those images they need to be represented for a computer to understand what's on there.
Yeah.
If you just look just at pixels, that's not really helpful.
Mhm.
So embeddings is basically you take as input the image, there is a model, and that will output an embedding. Which would represent then the semantic meaning of the image. Basically what it means. So these two couches, for example, if you take a picture, if you would put it through a model, you would, color is of course part of the semantic embedding. So there they are different, but they're both couches. So they are somewhat close in, you can call this it's a vector space. So they are somewhat close to each other. So it will be closer to each other than, for example, this camera.
Mm-hmm.
Not sure if I'm allowed to say that we are here and it's a camera.
Go ahead, do your thing.
They should know.
I hope so.
But they are closer to each other than, for example, a camera, but they are based on color maybe a bit different. Like if there was another couch of the exact same color, they would be closer to each other than this blue couch.
Yeah.
So this would help you like finding similar products using like a smaller space to search.
And this is pure math, right?
Yes.
Oh, this is
Yes, it's also like a lot of the core technology of all the large language models as well. That they are using in some way embeddings as well.
and that would mean that every image would generate an embedding.
Yes. So the 200 million images that we process basically means we have one BigQuery table with more than 200 million embeddings in there.
Oh wow. Okay.
Then
That's new for me.
these numbers are amazing. Huh? And these embeddings you compare and see if they are.
Yes.
You're
Yeah.
the
So
same?
there are there are algorithms that are optimized for this. So you
Mhm.
can of course brute search. So you can do like compare every embedding with every other embedding.
Mhm.
Meaning if you do one search, you have to compare to 200 million other images. That's not doable.
No.
That would take way too long. So there are like actual smarter people of other companies that already solve these kind of challenges. So there you can do first some kind of clustering. So you have those 200 million embeddings. Well, each embedding can be assigned to a certain group. So let's say those 200 million are brought back to only 1,000 groups. So then if you do a search, you take that one image, you compare it first to the 1,000 groups. So you can take the average embedding, for example, of the group. That will only do a comparison 1 to 1,000. You take the top 5 closest groups, and then within that group, you're only searching. So then you do a 2-step approach where you really limit the search space by making a bit of, you lose maybe a bit of accuracy because you're not comparing to all the 200 million, but at least you're able to finish the search within the night.
Yeah, indeed, to make it at least a bit scalable.
Yes.
But why would you want to compare these embeddings, these images? What would be the reason for it?
Yeah, so that indeed is to get like actual matches. So to show the whole process, what we do is we have images from competitors.
Yeah.
So then we just let's say this couch is on a competitor website.
Oh, yeah.
We get the image.
Yeah.
We have all our images on Bol already embedded.
Yeah.
So we embed the new incoming image. We compare it to our 200 million images, and we can get back the top 10 candidates that we think, okay, these are most likely the same products. And you get like image distance. So let's say if the image distance, meaning how far away are those vectors, those embeddings, if it's very small, so let's say between 0 or 0.5 or whatever, then we say, okay, this is most likely a match. And then we have multiple steps in the pipeline that are then comparing more than just the image, right? It's not just the image. The iPhone 16 gigabyte is the exact same image as the iPhone 32 gigabyte. So then after that, we are also checking more. But this is the first step.
Okay.
Yeah, that's awesome. And the huge model, like, that's only processing the embeddings, or do you enrich it later on with, let's say, another iteration of the titles? Do they match, or are those also the same? Or is this purely based on the embeddings of the image?
Yeah, so the first getting the first top X candidates is done with an image search. And this is because we think that it's more reliable. And then you have closer candidates using images because they're less likely to be contaminated, let's say. And then deeper down in the pipeline, so when we first start, let's say that for a product, we're looking for a match, and then we get the top 10 matches based on images. Then we take this one product and these 10 matches, then we put them through another unstructured data comparison, and this is where we look at titles. But what we do with titles is a little bit different than what we do with image embeddings. So with image embeddings, indeed, we use a pre-trained model that we do not necessarily do anything with, and then we use the embeddings generated from that. Whereas with titles, we have a model of our own. So where we can sort of input these two different titles, and we have trained the model based on the past matches that we have. So we already have a lot of matches indeed with these ENs, with European article numbers. So we know which products with which titles are a match of each other. So we have trained, or let's say fine-tuned, an existing language or natural language processing model to fit into this use case of determining whether two titles belong to the same product or not. So that is the later step after we have weeded out the unnecessary or like irrelevant products, and we have these top X candidates that we want to search for. Then we put them into this title comparison model. And after this, we will get a prediction. And using the image distance and the title comparison prediction, we make a decision. Then we say, okay, if we have a step on top of that as well to learn from these numbers, and then we can make a decision. These products are a match or they are not a match. And for each candidate product, of course, we want to have only one match. So we will take the most likely.
Yeah, I see. For me now, finally, it makes sense. Like the name Cupid, like matching. You see where that's where it originates from.
Yes, that's where it comes from. Indeed. So we do the happy matching.
I like
products.
Now I get it. I thought maybe it was an acronym or something, but it's the matching Cupid.
Matchmaker.
Exactly.
Nice. Because we just talked about the model, of course, and if we talk about like the enablers that this model can bring, or the features it can actually bring to the value propositions, like, can you shed a light on it? Like, what does it enable?
So I think indeed the whole project started partly as a YP project, but also because we were in pricing and there was this big gap of products not being matched. But while we were building the pipeline, at some point we were also playing around with parts of this technology, and we're like, hey, if we change only a small thing, we can actually use the same stuff, the same technology, but with a different use case. One of the examples, so instead of matching with competitors, you can also match with our own catalog. So we can just use an image of our own catalog, search through our 200 million images, and see if we find exact matches. Because that would mean there are duplicate products on our web shop. And that's, of course, not ideal. We are a platform and we want to have more competition on the platform because that would help the customer, because if there's competition, the retailers will compete for price and delivery time, and then the customer will get like the best price and delivery time available. So actually we thought, okay, let's run the pipeline, but then instead of using as input competitor images, we use as input our own images. And that has been running for a few months, where we deduplicated our web shop. It was really impactful, and we deduplicated quite some products. So that was one of the use cases. With only changing one input, we could use the exact same technology, which was really cool.
Cool, yeah.
Another one is they are experimenting now with it. So this is not our technology. They are not using our data, but it's the same type of technology they are doing. So image search. So for the customer, they are now introducing this to the app. Slowly roll out, of course. But they are the idea is you also have it on Google image search. You can just take an image of something and you can just search for products. So instead of what we now do every day at midnight, we run this batch job. here you have it real time. So it's somewhat the same technology. You take an image, you embed it, you search through all the embeddings, and you can get back the top K candidates. Of course, here you're not really exact matching, maybe sometimes, but it's less bad if it's not exact, right? So for us, we really needed to have the exact same product. So there we added one part of the pipeline to compare titles. But here, if they are visual similar, that's also what the customer most likely expect. Like they don't care if you take an image of an iPhone, you get back the iPhone 128 and 256. That's probably what they want.
Yeah.
So there, it's not really the title comparison is less needed. But the first step is most likely the same.
Yeah, makes sense.
Don't think did I forget?
No, I think those are the most impactful.
Yeah, you tell it like it's a big thing, but I think this is indeed super cool. And honestly, I'm not sure if you used it, but the image search as well, just the concept of indeed these embeddings and how the good technology nowadays already is to just identify duplicates or similar products. I was mind blown.
Yeah, no, for sure.
Really mind blown.
What's also mind blowing that I understand the guys in the way you guys explained it. It's like very clear explanation. Like I could tell my grandmother this. She probably could also understand it. Well, it's actually very complex, right? It's like not simple stuff, I would say.
Yeah, it's not necessarily super simple because of the scale, but the tools are there.
Yeah.
So we have built on a lot of existing technology. We just combined it in a way that in the company we hadn't really done to this scale before.
Yeah.
But yeah, I think putting it at scale was the main challenge for us. Okay. So a lot of the components that we have used are publicly available. All these models for embedding, so these transformer models, there are a lot of really good ones out there. And also the algorithms for doing searching. We did build our own title comparison model, so there is some extra added sort of data science done. The rest is kind of combining these elements in a way, which of course brought its own challenges because of the scale that we have.
Yeah. Can you maybe elaborate a little bit more about the scalability challenges?
Yeah, so when you work with like these millions of different images, and first of all, how you process them, you need to be able to be reactive. And for example, what we do is we look at incoming images every day, and you need to sort of make sure that it completes in time for it to then propagate to the rest of the organization as well. So there, of course, we are using a bunch of GPUs and some machines that can handle the scale at which we process, but also storing these and then accessing these later became a big challenge. For storing, we rely on BigQuery, and we also have all this data sort of available to the rest of the organization to use from there as well. And to do the comparisons between images, we have divided our images based on shops. So then when we look at competitor images, for example, we try to guess from their category which shop they would belong to. And then we only limit our search within that shop. And then we do the algorithm that Thijs talked about, where you do the clustering. So we do extra steps on top to be able to limit our search space as much as possible, because otherwise it's not that feasible to search from the whole list of products. There are other sort of options. There are even smarter algorithms to reduce the size of these search spaces, but they usually lose a little bit of the accuracy. So if you would have like an index, like a vector embedding of, let's say, a size 100, these sort of reduce them and quantize, it's called quantization, quantize them to a size where they lose some of the information, but when done the comparison, they still give good results. But we didn't in the end go for this because we want to have the highest accuracy. And because we are doing things in batch and we are doing this every day, we still have 24 hours available to us, right? So we still kept the highest precision that we can find. and sort of this whole pipeline in a day takes some hours, but this is how we kind of overcame the scale issue.
Yeah.
And
Nice to
then
hear. Yeah.
besides accuracy as well, I think cost is of course also quite important, because you can also say, okay, let's just get bigger machines and more GPUs, and you can probably use the same algorithm. But then costs spike a lot, of course. I think at the beginning we made a cost estimation of the whole project. We thought, because we calculate, okay, how many images do we need to embed, etc. How long will this take? I think we guessed it to be plus minus 15K to run the whole project.
I
think in the end
just
we
the project.
To embed, process all the images. Like the initial batch is really big, right? Because now we are just looking at newly incoming images. But of course, the first one is really, really big. We had a backlog of 200 million plus images to process.
Yeah.
So this would be immense amount of time would take an immense amount of time. I think because of indeed we optimized it quite a lot. In the end, it costed us around €1,000 to embed the whole catalog.
Yeah.
So
Doable.
That's impressive.
So either we were really bad at estimating cost, or we spent the right amount of time on optimizing.
I would pitch the second one.
Yeah, same.
That's impressive. Also, like hearing how you both talk about not only the data science part, but also the GPUs, the CPUs, the resource management, how you scale to larger chunks. I think that already goes beyond. Maybe my role interpretation of data science is incorrect, but it looks like the team that you have built is really multidisciplinary. That's a hard word.
Yeah, I know.
Multidisciplinary.
Try to avoid it.
Yeah, thank you. But that's really cool to see, though. Like, because how did this came? Like, is this something you guys liked, or was it part of your role already?
I think it came from. So there were attempts to do this before within the organization, sort of trying to match products, trying to deduplicate. There are some dead repositories somewhere from like years and years ago. So this always was an idea that, hey, we can do more with the unstructured data that we have. We can do more with sort of this searching capability. And parts of this were already existing in the organization. So we had the team that we merged with, Team DS1, they did have some applications that were just working on titles and title similarity. So we knew that, okay, this is a possibility, but nobody in the team really had the experience to do this. So it was, I think, a big learning for all of us by trying, reading more, failing, and then trying again. Just trying out these technologies, like I said, at first on a small scale, even on a local machine. And then, okay, this kind of works, this doesn't work, a lot of manual checking. And slowly we built up the experience necessary to build this on scale. So I think it came from both, hey, we should try this because we know that it's possible. And also, hey, we want to learn more about this. And I think this is also where a little bit of the boundaries between data scientist and engineer kind of disappeared a lot for the team. I think this is also where you learn a lot about engineering and machine
That's why I
learning
made the joke at the start of the talk. I learned engineering on the job. That was exactly because of this.
So like we sort of did all of this because there is a lot of like provisioning. There is a lot of, hey, which type of algorithms shall we use and how can we deploy them? There are ways to do vector search within Postgres as well, for example. So you can use a Postgres database to do vector search, but that is a whole thing on its own with like extensions and extra costs because you're hosting these huge vectors. So a lot of it was indeed, let's see what's available out there and let's see what can we use already available within our landscape.
And just a note, vibe coding back then was not a thing.
That's
so
not a thing.
No.
There was still a lot of Stack Overflow and
a
lot of Medium pages.
I love this approach. Very experimental, starting small, learning by failing. It's like a classic how you want to work, right? So
yes,
exactly.
It was a lot of fun.
With fun and also good results, right? Great results, actually.
Exactly.
Yeah.
I forgot actually about one use case. So I don't know, just going back to it, but assortment quality also uses this a lot. So what you can imagine, like at some point we have products that we don't want to sell on our platform. And
Oh, yeah.
here we do actually exactly the same. So we for that product, sometimes there is an image available. We just use that image to search identical products as well on our platform. Like, hey, then this is flagged and it goes to a moderator.
Oh, wow.
So then this will help you as well to make the platform more safe.
Yeah.
Oh, okay. Yeah.
It's
course.
really smart.
Yeah.
Yeah, it's really a huge enabler though for all of these initiatives.
Exactly.
Awesome work.
Yeah.
Thank
Yeah.
you.
Could maybe also be used for recommendations. I like this sweater. Can you find something?
Yeah.
Yeah, indeed. So we also, that's why we know a bit how image search is doing it as well, because at some point we were also contacted to think along and see, can we set up a POC? So there was this one other engineer that was really enthusiastic about the technology, and he was playing around with the technology as well. So at some point he was creating this temper monkey plugin. Where you can just on a product you could swipe to the right, and you get like similar products based on the image. It was really cool
Nice.
to see.
That's cool. Yeah.
Yeah. Sounds
This
even
is-
more like Cupid.
yeah. Nice.
This technology is sort of the basis indeed for a lot of things that are already powering the platform, like search and recommendations in one way or another,
Yeah.
especially from a semantic level,
Yeah.
rely on this technology, like creating these embeddings and sort of comparing them. So indeed, I think as a company, we currently do not have a one way of defining which products are similar, but for each use case, sort of we have built this notion of, okay, these products are similar and you can use these data points to define that similarity. So I think the options are all there within the company. It's just coming up the use cases. That's the next challenge.
Yeah.
Like, where can this be applied? How can we utilize these technologies the best? And I think indeed the visual search is now the latest sort of push for this.
Yeah.
And already working really well. I don't know if we're allowed to really promote it now. I don't know if the external communications went out, but working
knows?
quite well.
Yeah, it is. Yeah, really nice though. I really want to thank both of you. Learned a lot on data science today, but also I'm getting way more curious because I know what you guys are working on right now. So I would love to invite you for hopefully quicker than 1.5 years later, but to hop on anytime if you have another cool project to share.
Yeah.
Because it's just super interesting what you're doing.
Cool. Thanks for having us.
Yeah, thank you so much for having us.
Yeah, it was
Anytime.
our pleasure. Yeah.
Thanks.
Great,
Thanks
guys.
a lot.